Hi guys. So in the last video, we were able to solve our first example using Buckingham's Pi method of dimensional analysis for the drag force on a body in a fluid medium, okay? So we're still going to solve problems in this video, but this is not going to be the same one we did in the former lecture. This is going to have more variables and be a bit more complex than what we're used to. But the aim at the end of the day is to be able to be more confident in solving Buckingham's Pi method and also be proficient at dimensional analysis, okay? So let's get straight to work. The discharge Q, so let's highlight every variable we come across. The discharge Q of a centrifugal pump depends on the mass density of the fluid rho, speed of the pump N, diameter of the impeller D, manometric head H of M, acceleration due to gravity G, and the viscosity of the fluid mu. Show that Q is equal to ND cube, phi of GH over N squared D squared, and mu over rho N D squared. Wow. So this is a fairly complex dimensional analysis question. We're going to approach it the same way we should approach every question with Buckingham's Pi, okay? And the first step is always to list every variable. List all the variables you have in your problem statement. All right, so let's go. The first one we have is the discharge Q. So this is our dependent quantity. Okay, I'm going to have to write the dimensions of this. So Q is a discharge, so that's volume per time. Cool. All right, so the mass density of the fluid rho. So we're very familiar with density now. So this is the mass per volume. The speed of the pump N. Okay, so this could be L per time. But I'm going to have to stop this here. You know, we've been solving questions on dimensional analysis since, and every time we've come across speed, we've always described speed as the dimensions for speed as L per time squared. But with Buckingham's Pi, we have to be careful and take into notice the context of the question. So what does that mean? We're dealing with a centrifugal pump, okay? So for those of you that don't know, the idea of a centrifugal pump isn't necessarily to drive fluid from point A to point B, but to rotate in a certain direction, either clockwise or anti-clockwise, to generate some sort of angular torque, okay? Some centrifugal force. So since this is a centrifugal pump, we are not dealing with linear pumps that could take water from, let's say, the borehole to an elevation or bring it from a tank down. So that's a linear pump that moves from X to Y, a certain point. But a centrifugal pump turns the fluid around an axis. So that means whatever speed we're handling with when we're dealing with centrifugal pumps is going to be an angular speed. So N is going to be an angular speed, and the dimension of this is going to be radians per second, since we're dealing with rotation, okay? And radians, angles are a dimensionless quantity. So this is going to end up being t to the minus 1, since there are no dimensions for degrees or angles, okay? For angles are dimensionless quantities too. We handled that in the intro to Buckingham's Pi, okay? So that means the dimensions for N, the speed of this pump, is going to be t to the minus 1, okay? So take notes of that when encountering a question like this, okay? So let's keep that in mind and learn to take questions into context. So N is going to be t to the negative 1. The diameter of the impeller D, so this is a length as usual. The manometric head, so this is H of M, and this is going to have unit L. So if you remember from Bernoulli's equation, is the sum of the pressure head, the velocity head, and the positional head. Okay, so head is always going to have, in fluid mechanics, head is always going to have dimensions L. So manometric head is a type of head you encounter usually when dealing with fluid mechanics and centrifugal pumps too, and it's the work done to raise a fluid segment, okay? Work done by the pressure. She's going to have L, dimensions L. Acceleration due to gravity, we're familiar with this, so this is length per time squared. And the viscosity of the fluid mu is going to be mass per L per time. Okay? Really cool stuff. The first step, done. Second step, counts the variables. So n is going to be equal 1, 2, 3, 4, 5, 6, 7. Number of independent variables. Look at it. We have m, l, and t. And l here is raised to power 1. L here is raised to power minus 3. T here is raised to power minus 1. T here is raised to power minus 2. So the safety of that is just to check that there are no hidden repeating motifs or repeating groups of ml and t. So it's usually safe to assume that m is equal to 3, okay? So the number of pi groups is going to be n minus m. So which is 7 minus 3, which is 4. So that means we want to end up with four pi groups in this problem, okay? We've handled the difficult parts of the introductory part of setting up our problem. The next step is to determine our scaling variables, okay? So determine our scaling variables. Remember, for scaling variables, as we covered in the introduction, we need a geometric term, we need a kinematic term, and we need a dynamic term. Okay, so geometric term is going to handle length, this is going to handle time, and this is going to handle mass for each of our 3 fundamental dimensions. So looking at this, we're going to have to pick between the diameter and the manometric head. So we're going to pick the simpler, most common one, diameter d. Kinematic is our rate, so we're just going to go for speed straight up. So that's going to be n. And dynamic is where our mass gets introduced, and we have to choose between viscosity and density. So we usually go for density in scenarios like this. So these are our 3 scaling variables for this problem. It's very important to keep in mind and not lose track of the steps to take when solving Buckingham Pi questions, okay? No matter how big the question is, every problem you're going to encounter is going to use the same steps. List your variables, identify the dimensions, determine the total number of variables, determine the number of independent dimensions, find the number of pi groups, since there's going to be n minus m, then choose your scaling variables. And you see that once we've done this, the rest of the solution from this point onward is going to be rather straightforward, okay? So let's go to find and creating our pi groups using our scaling variables, okay? So the first one we handled, remember, scaling variables are going to be d, rho, and n and rho, okay? Diameter, angular velocity, and density. So let's find the first pi group. Remember, we said m is going to be raised to 0, l to 0, t to 0, and this is going to equal, so we're going to pick the first non-repeating term, so that's q. So that's q multiplied by d raised to power a, n raised to power b, rho raised to power c. We're going to have to expand this dimension, so that's going to be q is the discharge rate, so that's l cubed per time. D is a diameter, L to the A, N is time to the minus B. So, we're going to do T to the minus 1 raised to B. So that's going to be T raised to power minus B. So that's N. And rho is going to be density raised to power C. So that's going to be ML negative 3 raised to C. So that's M to the C, L to the minus 3C. So that's M raised to power C, L to the minus 3C. So that's going to equal M to the 0, L to the 0, T to the 0. So you could group like terms to make this more intuitive for ourselves. M to the C, L to the 3 plus A minus 3C. So that's 1, 2, 3. And T to the minus B. Okay, so let's get to work. M is for 0, L is for 0, T raised to power 0. So solving this, our simultaneous equations are going to look something like C is going to equal 0. We can tell that easily. So comparing B, minus B. So this is minus 1 plus B. Okay, so it's very important that you backtrack and check your steps often when dealing with Buckingham's pi. So minus 1 minus b is equal to 0. And then 3 plus a minus 3c is equal to 0. So if we were to solve this simultaneously, we'll establish that c is equal to 0. Okay, m to the 0 is equal to m to the c. That means c has to be 0. So 1 minus b, minus 1 minus b is equal to 0, meaning that b is equal to negative 1. And then, okay, so b is equal to negative 1. And then solving for c, so that's 3 plus a minus 3c is going to equal 0. 3c is 0. So that means 3 plus a equals 0. A is equals to negative 3. So we have our exponents for the first pi term. A is going to equal minus 3, b is equal to negative 1, and c is 0. So what does it mean when we have an exponent of 0 for our pi term? That means whatever variable is associated with it disappears entirely. Okay? So remember, pi 1 is q, our discharge. D to the a, m to the b, rho to the c. Okay? Substituting our exponent. So that's q times d raised to power negative 3 times n raised to power negative 1 times 0 raised to power 0. So this is going to just turn to 1. And the entire term is going to disappear. Simplifying the fraction. So that's going to be q over n d cube, which is our first pi term. Okay? So these are the steps in solving dimensional analysis, finding the pi term. It's the same format throughout. Keep going. Be careful with the algebra. It's very easy. It's quite easy to make mistakes when handling this. So let's clear the workspace so we can handle the next pi term. Okay. So let's get straight to it. So we go for pi 1. So this is a repeating variable. So we go for pi 1. This is a repeating variable. The repeating variable, the repeating variable. So we have to do for the remaining 3. So h of m, so that's pi 2. So pi 2 is going to equal h of m d raised to power a, n raised to power b, rho raised to power c. Okay? M raised to power, let's get a line in here. Okay? So m raised to power 0, l raised to power 0, t raised to power 0 is going to equal, recall h of m is our manometric head. Okay? The work done per unit weight of the fluid. So that's going to be h. So there are no exponents on the non-repeating variables. Multiplied by d raised to power a. So d is the length. So that's l raised to power a. Multiplied by n raised to power b. So n is per time. So that's t raised to power negative b times rho raised to power c. So remember, that's our density. So that's going to be mc l to the minus 3c. Okay? H is the length of dimensions l. So this is going to have to change to l. Gathering like terms together, we will end up with m to the c, l to the 1 plus a minus 3c dot t to the negative b. Okay? So m0, l0, t0. So let's equate the variables. So c is going to equal 0, and minus b is equaling 0, meaning b is equal 0. So we can just compare this with the appropriate term. Look at m is here, raised to power 0, and this is the only m term. T is here, raised to power minus b, and t is 0 here. So that means they have to be 0 for dimensional homogeneity to be conserved. Okay, so all we have left is the exponent of a. So we can say 1 plus a minus 3c is equal to 0. This is 0. So that means a is equal to minus 1. So if we were to reinstate our pi term, so that's h of m d raised to power a is minus 1. Okay, n raised to power 0, rho raised to power 0. So that means our pi 2 is going to be h of m d to the minus 1, which is the same as h of m over d. Okay, so now that we solved for pi 2, let's get our third pi term. So pi 3 is going to be for the third non-repeating variable, so that's g. So pi 3 is going to be g d to the a n to the b rho to the c. Okay, so know that these are all 0. You need to call g is an acceleration, so that's lt to the minus 1. D is a length, so d is a length, so that's l to the a. N is a speed, so that's t to the minus 2. And rho is density, so that's m to the c, l to the negative 3, c. Okay, so getting our equations, or simplifying this, bringing this together, so that's going to be m to the c, l to the 1 plus a minus 3c. Okay, and t is going to be minus 1 minus 2 b. Okay, because n is raised to power b. L to minus 1, L to the a, this is a rate t to the minus b. Okay, yes, t to the minus b. So t raised to power minus 1 minus b. That's these. So solving a simultaneous equation, we can establish again that c is going to be 0, since this is the only m term. So solving for b, so it's going to be minus 1 minus b is going to equal 0. Minus 1 minus b is going to equal 0. Lt to the minus 1. Lt to the minus 2. Pardon me. Okay? So g is an acceleration. Small g is acceleration due to gravity. So that's going to be t to the minus 2. Okay? So our second simultaneous equation, minus 2 minus b is going to equal 0. So that means b is equal to negative 2. And solving for a, 1 plus a minus 3c is equal to 0. C is equal to 0, so that means a is equal to negative 1. Okay? Substituting these guys in, so pi 3 is going to equal g, so d is raised to power a, so that's d to the minus 1. N is b, so that's minus 2 squared. And rho is to 0, so that means pi 3 is going to be g over d n squared. Alright, and we're making progress with our analytical journey. The last step we have to solve for is the last dimensional term, which is mu. So that's pi 4. So pi 4 is going to be mu. Then the same procedure, d to the a, n to the b, rho to the c. Okay, we know how this goes. M L0 t to the minus 0. So mu is viscosity, so that's m L to the minus 1 t to the minus 1. Okay, these are length, L to the a. These are speeds, t to the minus b. And this is m to the c, L to the minus 3 c. Okay, so setting up assignments, gathering these guys together to make calculations easier for us. M to the 1 plus c, L to the negative 1 plus a, negative 1 plus a, negative 3 c. And t to the negative 1, negative b. So minus 1 minus b. Okay, so let's get to work solving this simultaneously. 1 plus c is equal to 0, meaning c is equal to minus 1. Minus 1 minus b is equal to 0, meaning b is also equal to minus 1. Okay, so solving for L, that's the diameter. So that's minus 1 plus a minus 3c is equal to 0. So that means a is going to be 3c plus 1, which is minus 3 plus 1, which is minus 2. So that means a is equal to negative 2. So substituting our values for pi 4, so that means pi 4 is now going to be mu times d raised to power a, so that's d raised to power negative 2. So that's over d squared. N raised to power b, So that's n raised power negative 1. And rho raised power c. So that's c raised power negative 1. So let's rewrite this afresh so that we can be more confident we can have a clear view of our solution. So remember, we'll go for pi 1. Pi 1 was q over nd cube. So that's q over nd cube. Pi 2 was h over d. So that's the manometric height over d. Pi 3 handled our acceleration due to gravity. So that's g over d n squared. And pi 4 was what we just got for the viscosity mu. And that was mu over rho nd squared. So that's mu over rho n d squared. So we have done the most complex part of our equation. So remember, our pi group with the dependent variable is going to be what these guys are a function of. So if we were to write this down, so we would say pi 1 is a function of pi 2, pi 3, and pi 4. So expanding this, we're going to see that q over nd cube is a function of manometric height over diameter, acceleration due to gravity over diameter n squared, and mu divided by rho. Okay, so this is rho. Mu divided by rho n d squared. And we can see that we're getting close to what our solution looks like. So if we want to identify and make this subject of formula, if you want to isolate the discharge q, that means you're going to cross multiply with the denominator of q. So that means q, our discharge, is going to be nd cube and the function of the manometric height over d, acceleration due to gravity over d n squared, and the dynamic viscosity mu over rho n d squared. Okay, and we're getting really close to our answer over here. Remember what we said, this phi, this Greek letter phi, is just saying that this is a function of the pi terms that are within, and we're getting really close. So if we were to leave this as a final answer, we would be absolutely correct. This is a correct solution using Buckingham's Pi method. Okay, but from solving fluid mechanics question, you come to understand that some variables are more important, or are important in more than one way. So I'm going to introduce what is known as the head coefficient. Remember, in the conceptual introduction to Buckingham's Pi method, I'll link that above, we covered the dimensionless constants and pi terms, pi groups that are common to fluid mechanics. That's where we mentioned Euler's number, Weber's number, Froude's number, Reynolds number, and Mach's number. So there are other coefficients that aren't as common as those 5, and the head coefficient is one of them. So the head coefficient, so you represent this by phi, okay, is a dimensionless parameter that indicates the pressure or the energy generated by rotating machinery. So we're dealing with a centrifugal pump, so we're rotating fluid, okay, over certain angles. So the head coefficient deals with the pressure and the energy associated with that rotation. So this phi, I'm not sure what this letter is. So this phi is mathematically described as acceleration due to gravity, h, all over manometric height. So acceleration due to gravity times manometric height over d squared n squared, where n is the rotation of the fluid. So you can see that if we leave this as a solution, we're absolutely correct. But since we're familiar with fluid mechanics, we know that the head coefficient is the product of g times the manometric height over n squared d squared. So if you come over to our dimensionless terms, if a is a dimensionless term and b is a dimensionless term, then a times b is also going to yield a dimensionless term. So we're able to identify that since we know these guys come together to form the head coefficients, so that's the pi group with the manometric height and the acceleration due to gravity. So that means phi. I guess that's phi. So that's phi is going to be a product of pi 2 multiplied by pi 3. And this is going to be a dimensionless pi group on its own. So it's solely for the purpose that we're familiar with fluid mechanics, and we know that we're able to identify where certain coefficients come into play. Okay, so the one that comes into play here is the head coefficient, and that combined pi 2 and pi 3 to a more common dimensionless constant. So you can make the assumption that given that the head coefficient phi is equal to g times h of m over d squared n squared, we can convert pi 2 and pi 3 to a singular dimensionless pi group, and therefore show that q is equal to nd cube as a function of g h of m, since we're multiplying the two pi groups together, over d squared n squared, and also a function of the dynamic viscosity over rho n d squared. Okay, hence shown. So since this is since this is g h of m over d squared n squared, or you can say since pi 2 and pi 3 combine, or you could say since pi 2 and pi 3 combine to form the head coefficient. Okay, so this is a valid solution to the problem, in the same way that this is also a valid solution. So just so that we can show beyond reasonable doubts, to show through Buckingham's Pi method that q is nd cube and the function of gh over n squared d squared and mu over rho n d squared. That's why we had to do what we did with this problem. So no matter how daunting this proof may look if you first encounter it, you just have to be calm and take the steps you're used to. Take the steps that we've established when covering Buckingham's Pi method. If you have a constant that you're not familiar with, it's perfectly fine to leave your solution in the natural way it ends up, even with Buckingham's Pi. So let's say pi of k is mu over rho VL. Okay, so you could leave, let's say if we were solving a problem and we ended up with something like this, we could leave it the way it is and it would be perfectly correct. But since we're solving fluid mechanics, we can identify that this is the inverse of the Reynolds number and replace this with the Reynolds number, since the inverse of a dimensionless parameter is also a dimensionless parameter. So it's more of pattern recognition, seeing constants you're familiar with. But if you don't want to take that risk, it's perfectly fine to leave your answers the way it is. So we've been able to show that q is what has been shown to be in the question using Buckingham Pi's method. So thanks for watching, and I'll see you in the next video.